Hi all. So we're continuing on here with our analysis of infinite series. And just as a quick refresher, so we started this unit looking at Taylor polynomials, and those were ways of taking not so pretty functions, so transcendental functions, and rewriting them as polynomials. And the more terms, the higher the order, the more accurate they were. And eventually the idea is to go forever and have a Taylor series that exactly matches your function. So for example, we now know how to write e to the x, sine x, cosine x, 1 over 1 minus x. We can write those as an exact infinite sum of polynomials. And that's pretty cool. And then, but we wanted to know that these sums only actually make sense if they actually converge, like if the sum actually exists. So the next question we started looking at is, okay, so given an infinite series, let's just answer this basic question. Does that given series converge or diverge? Meaning, when I add it forever, do I get a nice finite number that it converges? Or does it blow up to infinity or for whatever reason not converge to a nice number, meaning that it diverges? And we started by looking at geoseries, which are their unique little subsection of series. And a geoseries converges if r is less than 1 in magnitude and diverges otherwise. Then we looked at the nth term divergence test. And that basically said that the series will diverge if the limit of the sequence is anything other than 0. As a quick example here, if we took this basic series and we add it to get 0 plus 1/2 plus 2/3 plus 3/4 plus dot 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 dot. Eventually, as you get to infinity, n over n plus 1, that plus 1's insignificant, and I'm just adding 1 forever. So what's going on here? So the sequence converges to 1. The series, though, means that I'm adding 1 forever. So eventually I'm just doing 1 plus 1 plus 1 plus 1 plus 1, and that's going to go to infinity. So the nth term divergence test said that since the lim of my sequence here is 1, which isn't 0, then the series diverges. And if the lim of the sequence is 0, it could converge or it could diverge. We don't know. It's inconclusive. And that's why we need more tests. So last time we looked at the integral test. Basically, if the integral converges, the series converges. The integral diverges, the series diverges. And as part of that, you also introduced the p-series test. And so if an integral is some number, doesn't matter, but over n to the p, if p is greater than 1, it converges. P less than or equal to 1 diverges. P equals 1, that's 1 over n. That's the harmonic series. It diverges as well. But alas, there are more tests. Just using the integral p series geo and nth term divergence test is not enough to show if every single series converges or diverges. So off we go. Again, we're just trying to answer this basic question. Does a given series converge or diverge? So let's look at the series here, sine squared n over n cubed. And this is never strictly decreasing. You could see here it's the graph f. So I can't use the integral test. The limit as you go to infinity is 0, so the nth term divergence test is inconclusive. And this isn't geometric, so I can't do geo. And it's clearly not a p-test as well. So I need a new test. So here I have f of n, it's shown in purple. And I also have a graph of g, which is 1 over n cubed, which is green. Now, 1 over n cubed is a p-test. It's a p-series, p equals 3, which is greater than 1. So I know 1 over n cubed converges. So this green here, I know converges. Basically saying that this sum is small enough such that it's finite as I go to infinity. And then looking at this, I see that f is always less than or equal to g. Look at the graph, f is always less than or equal to g. You can tell by the functions too, sine squared n is always less than or equal to 1, and the denominators are the same. So if green, or 1 over n cubed, is small enough that it converges, and f, or sine squared n over n cubed, is always less than g, then just using a little bit of logic, I can say then that my series here, f, or sine squared n over n cubed, that must also converge. Let me reset that once more. G, 1 over n cubed, we know converges. It's small enough to converge, because p is 3. F is smaller than that, so f must converge as well. Likewise, we can look at this series here. And if I compare that, I don't know what that graph looks like. I guess it's here in F. I should make that purple, I suppose. And then I'd say I compare it to this G, which is 1 over root n. In this case, P is 1/2, less than or equal to 1. This diverges. So G diverges, which basically means that it's big enough that as I go to infinity, I diverge. F is more than that. So G was big enough that it diverged. F is bigger than that. F is going to diverge as well. So what we have here is basically going through the conditions of what we're calling here the direct comparison test. Basically means take your series, find something that looks kind of like it, and compare it to that. That's basically what we're doing. Because again, most series we can't actually find the sum anyway. We're just trying to figure out if it converges or diverges. So if something is less than a converger, it'll converge. Something is greater than a diverger, it'll diverge. But if something is less than a diverger, that's inconclusive. If something is greater than a converger, that's also inconclusive. So think about it this way. Let's say you and your friend take a test, and your friend does, well, you don't know what you got, but you know that your friend passed, and you know that you're smarter than your friend. So you know you did better than your friend. So your friend passed, you did better than your friend. Okay, then you know that you passed as well. Again, let's say your friend passed, but in this case, you're not as smart as your friend, so you did worse than your friend. So your friend passed, you did worse than them. You don't know. Maybe you just barely did worse than them and you passed. Maybe you just bombed it and you totally failed it, but you don't know. So if you did worse than someone that passed, that's inconclusive. Likewise, if your friend bombed it, they failed, you did better than them, then you don't know. Maybe you did way better and you passed. Maybe you did slightly better and you still failed. That's inconclusive. But if your friend bombed it, but you did worse than them, then you know that you failed as well. So it's basically the direct comparison test. Remember, diverge means big, converge means small, for lack of a better term. But if something's bigger than something that's big enough to diverge, it'll diverge as well. Now, something smaller than something small enough to converge, then it'll converge as well. And then just remember, the middle cases are inconclusive. So if something's smaller than something that diverges, we don't know. If something's bigger than something that converges, we don't know as well. Just one note that the series needs to be positive. Just a caveat there. So in practice, the only challenge here is really figuring out what to compare it to, and that'll come with practice. So that just like now, hopefully you're pretty comfortable figuring out what your U should be for U sub. Same thing here. With practice, you get pretty good at figuring out what to compare it to. As a hint, it's generally helpful to figure out and focus on which terms are dominant as n goes to infinity. And remember, if you get inconclusive, that just means use your new test, or if you're stuck using the comparison test, pick a different comparison. Make a different comparison. Inconclusive doesn't mean you did anything wrong. It just means you have more work to do. You have to do something else. All right. So we want to figure out if the series 2 over 3 to the n plus n converges or diverges. And so the series is not geometric. It's not P. I can't really integrate that. And as we go to infinity, the limit is 0. So I'm really out of test. So I'm going to do a comparison here. And the way I see it is I can make two comparisons. I could compare it to 2 over 3 to the n or with 2 over n. Basically, the numerator is what it is. It's 2. And the denominator has these two terms, 3 to the n and n. And let's just pick one. Let's just pick 2 over n. Let's see what happens. So 2 over n, that's just a harmonic series. Just 2 times 1 over n. That 2 doesn't impact it. So this diverges. And then our series is less than 2 over n. Why? Because the numerator is the same thing, but the denominator is bigger. I'm adding 3 to the n. So our series is less than 2 over n. 2 over n diverged. Being less than a divergent series tells me nothing. This is inconclusive. And it's not, doesn't mean my answer is wrong or anything. It just means that that's a bad comparison. It was inconclusive. So I guess I'm left now comparing it to 2 over 3 to the n. So the whole point is to compare it to something whose behavior you know. And 2 over 3 to the n, we know that's a geoseries. R is 1/3, which is less than 1. So this converges. And same analysis here. R series is less than 2 over 3 to the n. Because the numerators are the same, and in my series, I just have a bigger denominator. I'm adding n. So bigger denominator means you're smaller. So 2 over 3 to the n converged. I'm smaller than a convergent, which means that my series converges as well. This converges by DCT. So even though it takes practice to figure out what to compare it to, in this case, we actually probably should have figured it out from the beginning. Remember, you want to focus on the dominant terms. As n, so I had 3 terms here in this denominator, 2 terms. I had 3 to the n and n. As n goes to infinity, both go to infinity, but you'll recall from one of the first sections in this unit that exponentials are dominant. So even though these both go to infinity, 3 to the n is the dominant term. And that really should have been the giveaway, that should have been what I used for my comparison. But again, no worries if I did the wrong comparison. It just gave me inconclusive. All right, so another example here. So I look, so my numerator is just 1. And okay, so no test works here, so I'm going to compare it. My numerator is just 1. Denominator, n to the 3/2 minus 3n. 3/2 is clearly dominant there. So this is the square root of n to the 3/2, which if you do a little bit of math is n to the 3/4. So p is 3/4, which is less than or equal to 1, so this diverges. And now we do our comparison. So these two series are the same, but mine I'm minusing 3n. So if I got rid of that, these were the same. That was the comparison. So I have a smaller denominator. Same numerator, smaller denominator, which means that this is larger. That's why I have that inequality going this way. So my series is larger than my comparison. My comparison one diverged. I'm larger than that. So this series we know must diverge. Weird typo here. The ends seem to be missing. Apologies there. So this one you have to be a bit more clever. But as n goes to infinity, you get 1 over ln of n is 1 over infinity, which is 0. So that's not very helpful. I can't take the integral. So again, I'm going to have to do the direct comparison. And this one's tricky. This one's a tricky one. I'm going to just compare it to 1 over n. I'm cheating because I know what to compare it to. You wouldn't figure that out, probably. So you just got to pick something that we can evaluate. And after doing this, you get exposure to why this method would work. 1 over n, that's harmonic, diverges. And 1 over ln of n compared to 1 over n. Well, I know that n is larger than ln of n. Again, these both go to infinity, but I know that n dominates the log. So 1 over n should be less than 1 over ln of n. So 1 over ln of n is larger than 1 over n. 1 over n diverged, so 1 over ln of n must diverge as well by the direct comparison test, which I can say is DCT. All right, so let's get into some practice here. My assumption here is that you are working through these before listening to me. You really learn best by doing, obviously. So please hit pause and play as you are ready, but don't just be doing this alongside me. Like, make sure that you are trying these on your own first. My assumption as I go through these is that you have tried these already. All right, so number 1, we're told to use the direct comparison test. So we'll do so. I have 2 choices. I could compare this to 2/3 to the n or to 1 over n. All things equal, again, exponential dominates power, so I'm going to try comparing to 2/3 to the n. So this is GO Absolute value of r is 2/3, which is less than 1, so this converges. And 2/3 to the n over n compared to 2/3 to the n. I'm just dividing by n, so I'm getting even smaller. So 2/3 to the n converged. I'm smaller than that, so I converge by that comparison test. In B, I'll compare it to 4/3 to the n. That's a geo. R is 4/3 greater than 1, diverge. 4/3 to the n plus 5 is clearly greater than 4/3 to the n. I'm adding 5, so this will diverge by dct. Right, C, it looks like, again, I'm going to just try my advice of dominance. So exponentials are dominant. So I'll compare this to 2/5 to the n. R is 2/5, which is less than 1. That converges. And this series is certainly less than 2/5 to the n. It's the same thing, but I'm dividing by n. So it's getting even smaller. This will converge by dct. D sine squared. A good trick to remember is that sine squared, cosine squared are always between 0 and 1. So I'm going to compare this. I'm just going to call that a 1. 1 over 4 to the n. R is 1/4, less than 1 converges. And sine squared 3n is less than 1. So this will converge. Remember, sine squared, you may be thinking it's huge because it's squared, but sine squared is always between 0 and 1. So it's less than 1 there. On this right side here, so I get rid of that 3. It's just n over n to 3/2, which is 1 over root n. P is 1/2, diverge. And I'm adding 3 to that, so I'm getting even larger. So this is larger than a divergent, so it diverges. F, again, we'll just look at the exponentials or what's dominant. 3/5 to the n. R is 3/5, less than 1, converges. And this series is less than 3/5 to the n because the only difference is I'm adding n squared in the denominator. So denominator is getting bigger, which means it's getting smaller. 3/5 to the n converge. I'm smaller than that. I will converge. Dominant terms in the denominator just n squared. So 2n over n squared. That looks like 2 over n. So that's harmonic. Diverge. Only difference again is I'm subtracting 3n in the denominator. So my denominator is getting smaller, which means I'm actually getting bigger. 2 over n diverge. This is bigger than that, so this diverges. And as we go to infinity, that plus 3 doesn't seem to matter. So I get e to the n over square root of e to the 2n, which is e to the n. So e to the n over e to the n cancels. And I'm really left with just 1 over n squared. P is 2 greater than 1, converge. And again, only difference here is I'm adding 3 in the denominator, so my denominator is smaller. So smaller than a converger will converge. All right. So again, now you're going through any method that you want, but you can go here through number 2 and determine if these converge or diverge using any method. Again, please try these before listening to me here. All right. So A is a geo. R is just 4/5, which is less than 1. This converges. B, I'm going to compare to 1 over n. 1 over n diverges. It's harmonic. And ln of n over n is greater than 1 over n, because ln of n is greater than 1. So this is greater than a diverger, so it diverges by the direct comparison test. C is a p. P is 5, greater than 1. That just converges. D, I'm going to actually take the limit here. So as n goes to infinity, this looks like n squared over n squared, which is 1, which isn't 0, so this diverges by the nth term divergence test. So again, the sequence converges to 1, but if you add 1 forever, you diverge. E is a very hard one. Very hard one there. Basically, I'm going to compare this to square root of n over n squared, which is 1 over n to the 3 halves. You would not have come up with this on your own, so don't worry about that. P is 3 halves, greater than 1, so this converges. And the trick here is that ln of n grows slowly, so it goes even slower than any power. So this is less than that, so it's less than a converger, which converges. I assume at first most people compare it to 1 over n squared, which converges, but then you get more than a converger, which is inconclusive. Again, this is a hard one. Don't worry if you missed that. K, this is just the geo, where absolute value of r is 2/9. That's the one. This converges. F, so as you go to infinity, this looks like 1 over n, which diverges. And all I'm doing here is, the cosine squared is always positive, so I'm always minusing. So my denominator is getting smaller, which means overall I'm getting bigger than my comparison. Remember, if you got rid of that, n over n squared is 1 over n. So this is greater than a diverger, which diverges by dct. I guess I'm just going in any order here. L, I could do the integral test here and get that the integral diverges, even though it doesn't strictly go to decreasing as one of the requirements are. But I'm just going to take the limb here. N approaches infinity. And cosine n squared. N goes to infinity, and cosine is just oscillating forever. So this limit does not exist, which doesn't equal 0. So this diverges by nth term divergence test. Again, I'm going through these quickly, but hopefully you're taking your time practicing and pausing me as you need. G, again, sine squared is always less than 1, so I'm going to compare this to 1 over n to the 4th. P is 4, it converges. Sine squared is less than 1, so this is less than a convergent, so this converges. A direct comparison test. M here. So I'll compare to 1 over root n, which P is 1/2, diverges. And then I'm going to say that ln of n plus 2 over root n minus 7 is greater than 1 over root n minus 7, because ln is greater than 1, which in turn is greater than 1 over root n, because I'm just subtracting denominator, which means smaller denominator, bigger overall. So I did a two-step comparison here, but nonetheless, I'm greater than a diverger, so this diverges. And then h here, if we take the limb as n approaches infinity, e to the infinity is 0, plus 4 is 4. So this adds 4 forever, so it diverges by the nth term divergence test. And likewise, take the limit as n goes to infinity, you get e to the 1 over infinity, which is e to the 0, which is 1, which isn't 0, so this diverges by nth term divergence test. I is a geo where R is 2/3 over 3/4, which is 8/9 in magnitude, which is less than 1, so this converges. O, so remember your dominant term is that exponential, so I'm going to compare this to 7 over 3 to the n. That's a geo where R is 1/3 and converges. Only difference here is I'm adding n to the denominator. Bigger denominator, smaller overall than a converger. So that converges by direct comparison test. J you can compare to 1 over n cubed as e to the negative n squared, that goes to 0. 1 over n squared, p is 3, so this converges. And then just do your comparison. Smaller than a converger, it converges. And then lastly, you can compare this to 2 over 2 into the fifth, 1 over n to the fifth. P is 5, greater than 1, converges. Only difference is I'm adding in the denominator, so I'm smaller. So this will converge by dct. All right, so we went through a lot here, but the direct comparison test is a way when the geoseries doesn't work, n-term divergence test doesn't work, integral p-test doesn't work. Basically, compare it to a different series. If you're less than a convergent series, you will converge. If you're greater than a divergent series, you would diverge. If still this doesn't work, then worry not. We have more tests to come that'll help us answer this simple question: does the given series converge or diverge? All right, everybody, be well. Take care.